Next, we are going to talk about nonlinear least square for the jaw data, which is also from the R book. We are going to run a nonlinear regression analysis to predict bone length using variable age. Next, let's see how the data set looks like. Okay, we loaded the data. And this is the variable age. This is the variable bone. And clearly, there's a nonlinear relationship between bone length and age. When age increases, bone is getting longer and longer, but eventually has this kind of pattern. Next, we are going to see the code to run the nonlinear least square regression. Here's the code. So we load the data and plot the data. And to make nonlinear least square, we use this function NLS, nonlinear least square. And Y variable, that's a response by, for this part, this is the nonlinear relationship. This part is according to the mechanism or certain knowledges we know about the growth of length, growth of bones and the age. This information usually is given in a question, or we need to have this kind of knowledge. So, for example, in this question, the ratio between length and age is given over here. So, only if we know this information, we can do nonlinear least square. If we don't know this information, okay, then we need to figure out this information based on the biological knowledge or based on or modeling knowledge. Usually this information is given, okay? Otherwise, we need to figure it out. That's complicated. And in this model, there are three parameters. One is beta sub 0, another one beta sub 1, and also beta sub 2. We need to input this in the R code. Let's go back to the R code. Right, so correspond, well, this part, there are three parameters, A, B, C. A is for beta sub 0, B is for beta sub 1, C is for beta sub 2. And also, when we run nonlinear least square, we need to, usually, okay, we need to set the initial values for those are initial values, basically some kind of estimate, very rough estimate. It's not necessary to be accurate, can be very rough. As long as the sign is right, it should be okay. So why we take those values according to the plot. So roughly, the data is the bone length is between 0 and 140. So A should be can be maybe a number of 60 or maybe a number of 100 or something like this. And for the others, okay, we need to know the relationship, the function. We need to know the shape of for the function, for the exponential function. Clearly, this one increase, but not increase that fast. So according to this data set, we determine to use the initial values as those values. If those does not work, okay, then we need to change them. Let's run it. You can plug in those values to this equation and see what is the roughly value for the bone. Okay, if that number is not that far away from a value in the data set, it should be okay. It should be okay. And make sure the sign of this one, especially for the right now here's negative C, right? So this C over here must be a positive number. So this one will be the exponential function of a negative value. So this one is going to, so this is important. So if you use a negative number over here, then you will have trouble. Sometimes the sum inside of the exponential function, the sum for the content must be correct. Otherwise, this may not run. Next, let's run the code in R, and let's summarize the result. Okay, wait a moment. There are some issues. The problem is that we need to specify DAT equals data equals DAT. So right now we did not specify the data set, right? So over here, the data set is called DAT, right? So we need to specify data equals DAT. And let's summarize it. And that's the result. The estimate for A parameter equals this number, which is not far away from 100. If you use a different one, you will still have similar estimates. We can try. Let's see. So right now, if we only select this one as 60 or even 50, 60, and B equals negative whatever, negative 5, negative 6, and this one equals maybe 2. That's pretty far away, right? Of the compared to the original selection. Let's see. Let's run it. Missing, okay, then it may not work. It cannot be that too far away. From 5, it should be okay. Well, still not okay. Negative 60 for the moment. Okay, so those values cannot be randomly selected. So be very careful. Oh, negative 10. So that's this one. Negative 12. Yeah, it should be okay. So if you did not select the right values, you need to try different values several times maybe. But eventually, once it runs, you can see if you can compare this, the initial results and those results, they're almost the same, right? Almost the same. 115.25, 115.25, something like that. Almost the same. So even use different initial values, the results should be the same. Almost the same, maybe slightly different. Very slightly different. And once we have the estimations, okay, sometimes we can use plot the curve to visualize the model. And let's see the R code. How to visualize it? We can calculate the fitted values. Oh, we don't need this. For the age is from 0 to 50, right? We can create the values for age in a total of 100 values from 0 to 50. We create a new data for prediction. Data frame age. Age is the variable equal those values, which is from 0 to 50. That's the same as the range in the data set. And we can predict the value for those ages. Fit is the result of the nonlinear least square estimation in those new data. But if we run this, and once we have this, because we already plot the data, plot x and y, so we already have the scatter plot. You can just add a line plots over it, and plot lines age against the prediction values, and let's run it. Okay, the age, the problem that data $ age, right? Because this is the age of the data. Oh, wait a moment, that's x, not e. Well, because we calculate, well, this is the predicted values for x, so here should be x. length x, y hat. So this is the predict the model, the fitted model, not the model, fitted model. Okay, let's stop here.